The history of humanity gazing up at the starry sky spans the entire course of civilization. We once wove myths beneath the starlight. We once measured time by the orbits of planets. We once believed the cosmos above was the epitome of eternity and tranquility, a realm governed by law and order. Planets strolled along their orbits, obeying the laws written by Kepler and Newton. Comets returned like punctual trains adhering to time. Asteroids mostly remained quietly within the main belt between Mars and Jupiter. Our solar system resembled a meticulously calibrated clock, each gear meshing with flawless precision. Yet this impression of tranquility was shattered in the mid-21st century. A series of unprecedented discoveries began painting a radically different picture. The solar system was not an isolated island, but a dynamic, vibrant environment intimately connected to the Milky Way. We began to realize we did not dwell in a tranquil garden, but alongside a bustling cosmic highway. This journey of discovery reached a dramatic climax in the autumn of 2025. The autumnal equinox that year should have been an ordinary marker on the astronomical calendar. Yet observatories and space monitoring networks worldwide detected anomalous disturbances. The initial signal came from an asteroid designated 2025 FA22. This mountain-sized rock, hundreds of meters in diameter, would pass extremely close to Earth. For the public, this was merely a noteworthy news story. Headline-worthy, yet unlikely to cause panic due to its safe distance. But within astronomers' internal communication networks, an unusual tension began to spread. For FA22 was not traveling alone. Following it closely were numerous smaller near-Earth objects, as if responding to some invisible rallying call. They arrived in rapid succession within an unusually narrow time window, crossing the cosmic space near Earth. Though their orbits varied in size and pattern, they seemed to have collectively agreed to make their debut during this crisp autumn season. This was no typical lone wolf visitation. Rather, it resembled the premiere of a meticulously choreographed cosmic theater production. Multiple performers took the stage in succession. Meanwhile, in another region of the sky, instruments aboard the SOHO spacecraft detected signals from a new comet. Named C2025-R2 Cygni, this comet was hurtling toward Earth from the depths of the outer solar system. Its brightness surged dramatically over several weeks. A gradually lengthening dust tail began to appear in telescope images, signaling its approach toward naked-eye visibility, adding another captivating dancer to this already crowded celestial stage. Yet the truly earth-shattering news remained tightly sealed within professional circles. A more astonishing and fundamental discovery was being confirmed in data from the Atlas telescope array in Chile. Initially, it appeared merely as a faint, moving speck in the stellar sea, indistinguishable from the thousands of asteroids or comets captured by automated sky survey systems. Yet subsequent observational data converged into a clear mathematical conclusion. This object, provisionally designated 3I Atlas, does not follow an elliptical orbit around the Sun. Its trajectory is an open hyperbola. This means it possesses sufficient velocity to escape the Sun's gravitational pull. It does not belong here. It originates beyond our solar system, from the domain of another star. It is a true interstellar visitor, only the third interstellar visitor confirmed by humanity. Moreover, its arrival coincides precisely with this anomalous cluster of asteroids. Preliminary chemical analysis reveals characteristics distinct from any known object in our solar system. Is this the greatest coincidence on a galactic scale? Or are we witnessing the first signs of some deeper cosmic law unfolding? Our familiar, predictable cosmic neighbors seem to be growing unfamiliar. A quiet country lane suddenly transforms into a bustling highway, its traffic patterns converging in ways that defy probability. Everything we've observed in the night sky this autumn diverges sharply from the norm. Astronomers have no choice but to begin asking that unsettling yet profoundly thrilling question. What exactly do the 3I Atlas and this accompanying celestial cluster signify for our solar system? The answer to this question will not merely concern scientific discovery, but will redefine humanity's place within the vast cosmos. Now, join me on this late-night exploration. We will examine each of these extraordinary cosmic events and peel back layer upon layer of mystery. Whether we ultimately discover this is merely a statistical anomaly or the beginning of something far more profound, it will mark a pivotal step in our species' journey toward interstellar understanding. The night sky in mid-September should have been tranquil, with autumn arriving in the northern hemisphere. The astronomical observation schedule should have featured only routine observations. In the databases of the International Asteroid Monitoring Network, the orbits of most near-Earth objects had been precisely calculated. Their trajectories for decades to come were firmly in hand. This mechanical precision was the pride of modern astronomy. Yet the cosmos never seems content to be fully predicted. It invariably reveals its unfathomable depths. When our confidence is at its peak, the events of autumn 2025 radically overturned our understanding of the solar system's workings. The density and anomalous nature of the astronomical phenomena unfolding during that period prompted astronomers worldwide to scramble to adjust their observation schedules and led the public to wonder whether we were witnessing phenomena beyond mere coincidence. The initial warning came from Asteroid 2025 FA22. This celestial body was first detected in early September by the Pan-STARRS telescope system in Hawaii. Subsequent orbital calculations immediately triggered the monitoring network's alert system. FA22's diameter was estimated between 130 and 290 meters, roughly the size of a small hill. It was set to make an extremely close flyby of Earth around September 20th. At its closest, it will come within just 835,000 kilometers. This distance is nothing short of perilous on an astronomical scale, only slightly more than twice the average Earth-Moon distance. Close enough to make global headlines, yet distant enough to let planetary defense experts sleep soundly. But what truly struck astronomers as unusual was not FA22's proximity itself, but the manner and timing of its appearance. FA22 is not a solitary traveler. It resembles more an advance guard of a cosmic procession. 3 days before its arrival, another asteroid, designated 2025 RJ2, had already slipped by unnoticed. Though RJ2 measures less than 100 meters in size, its flyby distance is even more heart-stopping, equivalent to just 0.78 times the Earth-Moon distance, approximately 300,000 kilometers. In astronomical terms, this was a near miss in cosmic scale, traced as a distinct path right at our doorstep. Yet these were merely the most conspicuous members of this anomalous cluster. Throughout these weeks of September, the data streams of the International Asteroid Monitoring Network simultaneously recorded dozens of additional near-Earth objects. As if by mutual agreement, they successively traversed the cosmic space near us. Each was meticulously cataloged and tracked, with their trajectories recorded by the Global Space Surveillance Network. These objects varied in size, from tens of meters to hundreds of meters, and their flyby distances ranged from beyond the Moon's orbit to extremely close proximity. Individually, each could be classified as normal NEA activity. But when concentrated within such a brief time window, the sense of clustering became impossible to ignore. The temporal compactness appears meticulously orchestrated, as if these ancient cosmic wanderers coordinated their arrival times to achieve maximum dramatic effect. Such anomalous clustering is exceedingly rare in observational history. Typically, NEO flybys are randomly distributed, following complex gravitational dynamics that have shaped the solar system's architecture over billions of years. Statistically speaking, the probability of multiple close flybys occurring within a short time frame does exist. Yet the scale of the September 2025 cluster appears to challenge the assumption of purely random distribution. More significantly, orbital analysis of these bodies reveals they do not originate from a single parent body, nor are they fragments from a single collision event. Instead, they exhibit distinct orbital characteristics and origins. This diversity renders simple explanations untenable. Meanwhile, regarding the observational capabilities supporting this anomalous cluster, human technology is undergoing revolutionary advancement. The Vera C. Rubin Observatory, which received its first light in June 2025, has already begun demonstrating the formidable detection capabilities of this revolutionary facility. During its initial 10-hour test observation, it captured data on thousands of new asteroids. Its vast field of view and exceptional sensitivity enable astronomers to monitor the sky with unprecedented precision. More eyes scanning the sky with heightened sensitivity reveal the true density of our solar system's population of small celestial bodies. Yet even accounting for enhanced observational capabilities, the timing of this cluster still feels too coincidental. It cannot be explained solely by observational bias. From a planetary defense perspective, this anomalous cluster offers a valuable stress testing opportunity. When FA-22 first appeared on the risk monitoring list, global planetary defense agencies immediately activated standard response protocols. As subsequent observational data poured in, its orbit was progressively refined, ultimately proving it posed no threat to Earth and leading to its removal from the list. Though this process spanned only a few days, it fully rehearsed the entire workflow from threat discovery to all clear. The communication protocols of the International Asteroid Early Warning Network were tested. Data sharing mechanisms between national observatories withstood scrutiny. Public communication strategies were practiced within a real news cycle. However, this exercise also exposed vulnerabilities in the existing system. Had FA-22's orbit been slightly different, or had its approach originated from the sunward side, our warning time could have compressed from weeks to days or even hours. Given its size and potential destructive power, such a short warning period would have catastrophic consequences. More concerning still, while our current deflection technologies have been validated through the DART mission, effectively deflecting an object the size of FA-22 still requires years or even decades of advanced preparation. The scenario of multiple objects emerging consecutively within this anomalous cluster raises a critical question. Can our monitoring and response systems handle multiple potential threats simultaneously? The scientific significance of this anomalous cluster extends far beyond planetary defense. It provides invaluable data for understanding the dynamical evolution of small bodies within the solar system. These clustered near-Earth objects serve as a statistical sample, enabling us to study the behavioral characteristics of minor bodies with different orbital types and compositions. Over similar timescales, their physical properties can be analyzed through spectroscopic observations. Their orbital changes reveal subtle gravitational perturbations. Their very existence narrates the history of the solar system's formation and evolution. Yet the most perplexing question remains unanswered. Why now? Why did these objects choose to appear collectively within the same time window? Is some unrecognized gravitational resonance at play? Is the solar system traversing a region of interstellar space with slightly higher material density? Or is this merely an extremely rare statistical fluctuation? As observational data continues to accumulate, astronomers have begun to notice a more unsettling possibility. This anomalous cluster of asteroids perfectly overlaps in time with another, even more extraordinary astronomical event: the arrival of the interstellar visitor 3I Atlas. When we examine FA-22's flyby, RJ-2's approach, and the cluster appearance of dozens of other near-Earth objects, alongside the arrival of 3I Atlas on the same timeline. The sense of coincidence grows increasingly potent. Either we are witnessing a highly improbable convergence of unrelated events, or some deeper cosmic law is at work. The answer to this question will determine how we perceive our place in the universe. It will also shape how we prepare for future astronomical events. In the following sections, we will delve into what would have happened if FA-22 had not safely grazed Earth, but instead collided directly. Through detailed simulations and scientific analysis, we will reveal the potential dangers of these cosmic wanderers and why their anomalous clustering warrants our attention. This wave of asteroids is not merely an astronomical spectacle, but a wake-up call, reminding us that the cosmos is both beautiful and perilous, and that human understanding has only just begun to skim the surface of its waves. As asteroid FA-22 dominated headlines with its close flyby, another distinctly different cosmic performer was quietly preparing its entrance deep within the night sky. The discovery of Comet C/2025 R2 Cygnus did not stem from deliberate ground-based telescope searches, but rather an unexpected find aboard the Solar Observatory spacecraft SOHO. The LASCO coronagraph, originally designed to observe the sun's hot plasma, accidentally became an efficient comet hunting tool due to its unique observational perspective. When a comet makes its final plunge toward the sun, the massive hydrogen atoms released from its icy nucleus under intense radiation create bright signals detectable by SOHO's instruments. This allowed the Cygnus comet to be captured despite numerous professional sky survey programs. This serendipitous discovery itself adds a layer of mystery to its story. Unlike precisely predictable rocky bodies like FA-22, Cygnus Comet represents a more elusive and unpredictable cosmic presence. By mid-September 2025, its brightness had increased to approximately magnitude 6, hovering on the edge of naked eye visibility. Under the slightly light-polluted rural night sky, keen observers began reporting a faint, fuzzy patch of light in the direction of Virgo, near the bright star Spica, against the faint reddish glow of Mars in the western sky after sunset. The comet's increasingly prominent and structured tail became an ever more striking feature of autumn nights. Comets are essentially dirty snowballs, loosely bound together by ice, dust, and organic compounds, with far less structural integrity than rocky asteroids. As they journey from the Oort cloud at the solar system's edge, their first approach to the inner solar system presents not only gravitational challenges, but also the harsh baptism of solar radiation. Solar heat drives the sublimation of volatile substances within the comet nucleus, transforming them directly from solid to gas. This process creates the comet's signature coma and tail, but may also generate immense internal stress. As Comet Cygnus continued brightening throughout September, astronomers simultaneously monitored its morphological changes. Any sudden brightening or distortion in shape could signal the nucleus is fracturing. Many comets discovered by SOHO fail to survive their first perihelion passage, shattering into countless fragments under the sun's scorching heat, leaving only a fleeting dust trail as their final testament. The physics of cometary activity involves complex sublimation interactions and the combined effects of temperature changes and solar radiation heating. Water ice begins subliming at approximately -70 degrees Celsius, while more volatile compounds like carbon monoxide and methane start releasing gases at greater distances from the sun. As these substances transition directly from solid to gas, they generate gas jets. These jets can significantly alter a comet's orbit through non-gravitational effects. This makes comet orbits, especially those of first-time visitors to the inner solar system, notoriously difficult to predict with precision. Whether Comet Cygnus would survive its early November perihelion intact remained unknown throughout September. Yet while this new comet captivated amateur observers, another more familiar cosmic figure waited silently in the background for its moment. Asteroid 99942 Apophis. This 400-meter wide rocky mountain, once topped all planetary defense concern lists, is now steadily progressing along its relentless path toward a historic encounter on April 13, 2029. At that time, it will fly past Earth at a distance of just 32,000 kilometers from the planet's surface, closer than most of our geostationary communications satellites, and close enough to be visible to observers anywhere on Earth, without optical aids, appearing as a bright, rapidly moving point of light in the night sky. The scientific value of Apophis's impending flyby lies precisely in the absolute certainty that it poses no collision risk. Years of radar observations and optical tracking have refined its orbital precision to a degree that rules out any possibility of impact in 2029 or the decades thereafter. This allows scientists to focus entirely on leveraging this once-in-a-lifetime opportunity to study the behavior of a large asteroid during an extreme Earth approach. Earth's gravitational influence during the flyby will be profound and lasting. Apophis will experience tidal forces strong enough to alter its rotation rate. Its surface features may be reshaped. It could even trigger global-scale surface material slides. The asteroid emerging after the flyby will be markedly different from its approach state. This presents a natural laboratory for studying how planetary gravity reshapes small celestial bodies on short timescales, providing a natural laboratory to seize this opportunity. NASA has repurposed the OSIRIS-RX spacecraft for the OSIRIS-APEX mission, setting it on a course to rendezvous with Apophis. The spacecraft will arrive at the asteroid shortly after its 2029 flyby, spending months meticulously mapping its surface post-Earth encounter, measuring how gravitational interactions alter its physical properties and internal structure. These data will be invaluable for future asteroid deflection missions, as they must account for how target bodies respond to externally applied forces. Apophis' approach coincides with the 3.5-year interval following the anomalous cluster of 2025 September, raising intriguing questions. Are we entering a period of heightened near-Earth object activity? Statistically speaking, asteroid close approaches lack a specific schedule. They are inherently random events, governed by the complex gravitational interactions that have shaped the solar system for billions of years. Yet the clustering of significant encounters within such a short time frame appears to challenge the notion of purely random distribution. Part of this apparent increase can indeed be attributed to observational bias. Major asteroid survey programs like Linear Pan-STARRS and the Catalina Sky Survey have vastly enhanced our ability to detect and track potentially hazardous objects over the past 2 decades. The Vera C. Rubin Observatory, which captured its first light in June 2025, represents another quantum leap in survey capabilities. Its vast field of view and sensitive detectors will rescan the entire observable sky every few nights, providing unprecedented temporal resolution for discovering new objects and monitoring known ones. However, enhanced detection capabilities alone cannot fully explain September's cluster phenomenon, nor account for the remarkable diversity of involved objects. Accompanying the approach of FA-22 and the brightening of C-2025-R2, dozens of smaller near-Earth objects traversed our cosmic neighborhood throughout September. Seasonal timing may offer clues about potential dynamics. Earth's orbital motion positions us in different regions of the inner solar system at various times of the year. Through different regions of the inner solar system, It is possible that September 2025 coincided with our transit through a particularly congested debris zone. Alternatively, the apparent clustering could result from complex gravitational resonances. Such resonances can synchronize the orbits of multiple objects on geological timescales. Comets introduce another layer of complexity to this cosmic choreography. Unlike asteroids, which follow relatively stable and predictable orbits, comets may undergo dramatic trajectory changes due to gas-induced forces and gravitational perturbations from giant planets. Long-period comets originating from the Oort cloud essentially arrive without warning. Their orbits have not brought them into the inner solar system. Over the past millennia or millions of years, the distinction between asteroids, comets, and meteoroids is often confused in public discussions about planetary defense. Yet these distinctions are crucial for understanding impact risks and mitigation strategies. Asteroids are essentially rocky or metallic mountains in space, following well-defined orbits that change slowly over time. Comets, however, are volatile-rich, unstable bodies, exhibiting unpredictable behavior due to outgassing effects. Meteoroids are merely visible optical phenomena, resulting from the combustion of tiny particles in Earth's atmosphere, regardless of whether their parent bodies are asteroids or comets. These diverse populations of minor bodies reflect the complex history of our solar systems, formation and evolution. The asteroid belt between Mars and Jupiter contains remnants of the planetary formation process, material that never successfully coalesced into planets. Comets, meanwhile, preserve pristine samples of ice and organic matter from the outer regions of the early solar nebula. Each group tells a part of the story of how worlds around a star form. Each presents unique challenges for planetary defense. As autumn 2025 progresses, the cosmic stage is set for more extraordinary revelations. September's familiar solar system objects will be eclipsed by an unprecedented visitor, a traveler entirely from another star system, bearing chemical signatures that will challenge fundamental assumptions about planetary formation and interstellar space. But first, this enigmatic voyager must navigate the complex gravitational environment of the inner solar system, while concealed behind the sun's blinding glare. When it finally reappears in telescopes' field of view in early December, 3I Atlas will prove unlike any celestial object astronomers have ever encountered. On the high plateau of Chile's Atacama Desert, the automated sky survey system of the Atlas Telescope Array operates as usual, night after night scanning vast swaths of sky, documenting countless stars and moving points of light. In early July 2025, the system captured what appeared to be an ordinary target, a faint speck of light moving across the stellar field. Its brightness was approximately magnitude 20, millions of times fainter than the dimmest stars visible to the naked eye. Initially flagged as yet another potential near-Earth object, it was assigned a provisional designation and entered the follow-up observation queue. In the initial days, it appeared indistinguishable from hundreds of other asteroids or comets discovered in the Atlas database. The automated system classified it as a potential near-Earth object requiring tracking based on its apparent motion across the sky. However, over the following days, as multiple observatories worldwide joined the observation effort to refine its orbit, astronomers began to realize they were witnessing something unprecedented. More observational data steadily poured in. The mathematical solution for its orbit grew increasingly clear. One parameter stood out prominently. Its orbital eccentricity was markedly greater than 1. In celestial mechanics, this is an unmistakable characteristic of a hyperbolic orbit. It signifies that this object possesses sufficient velocity to completely escape the gravitational pull of the Sun. This object does not belong to our solar system. It is merely a visitor, a messenger from interstellar space. 3I Atlas, the third interstellar visitor confirmed in human history, thus formally takes the astronomical stage. Its naming follows the convention of the International Astronomical Union. I stands for interstellar, while the number 3 indicates it is the third such object confirmed. Unlike previous interstellar visitors, 3I Atlas arrives at a perfect moment. Its orbit will bring it to perihelion in late October 2025, followed by its closest approach to Earth in December, approximately 18 astronomical units, equivalent to 2.7 billion kilometers. This distance is far enough to pose absolutely no threat to Earth, yet close enough for our most powerful telescopes to conduct detailed spectral analysis, as if the cosmos deliberately arranged a pristine sample from another star system, delivered to our astronomers' doorstep under optimal observation conditions, with ample advance warning. But 3 Atlas's orbit is merely the first layer of its mystery, as observational data accumulated throughout late summer and early autumn. This interstellar visitor began exhibiting characteristics challenging our fundamental assumptions about interstellar space and cometary behavior. Hubble Space Telescope observations provided an upper estimate for its nucleus size of approximately 5 to 6 kilometers, though its actual dimensions may be smaller, placing it within the intermediate range between typical cometary nuclei and asteroids. What truly distinguishes 3I Atlas from its interstellar predecessors is its pronounced cometary activity. Unlike Oumuamua, which exhibited no visible coma or tail, yet displayed puzzling non-gravitational acceleration, 3I Atlas displayed classic cometary features. As it approached the Sun, by September, ground-based telescopes could discern a distinct coma, a cloud of dust and gas enveloping its nucleus, along with an emerging, impressive coma structure. This cometary activity provided the first clues about the object's true extraterrestrial chemistry. When the James Webb Space Telescope pointed its powerful infrared spectrometer at 3I Atlas in late summer 2025, the results revealed a composition unlike any comet in our solar system. The object's coma exhibits an unusually high ratio of carbon dioxide to water ice, one of the highest CO2 proportions ever measured in a comet. To understand why this chemical composition matters, consider how comets form in typical planetary systems. Water ice condenses from the protoplanetary disk at temperatures around 150 Kelvin, corresponding to orbital distances of about 2 to 3 astronomical units from a Sun-like star. This is why most solar system comets, though formed in regions beyond Neptune's orbit, still contain substantial amounts of water ice mixed with other volatiles. Carbon dioxide has a much lower condensation temperature, only at distances exceeding 10 astronomical units from the parent star, where temperatures drop below approximately 80 Kelvin. Does carbon dioxide ice become the primary component of cometary ices? Even then, carbon dioxide typically constitutes only a small fraction of the water ice. The extreme carbon dioxide dominance in 3I Atlas indicates it either formed under conditions vastly different from our solar system, or underwent some subsequent process that selectively depleted water while preserving carbon dioxide. One possibility is that it formed in the outer regions of A, or a much larger planetary system. If the protoplanetary disk around 3I Atlas orbited a low-mass star, or existed within an unstable system hosting multiple giant planets, it could have formed in an environment where carbon dioxide ice was the primary volatile component. In such conditions, water ice might never have condensed in significant quantities, leading to the extreme composition ratio observed by the James Webb Space Telescope. Alternatively, this object may have undergone extensive processing during its long journey through interstellar space. Millions or billions of years of cosmic ray bombardment, potentially altering its surface chemistry through radiolysis. High-energy radiation breaks chemical bonds, If this process preferentially removed water molecules, while leaving carbon dioxide relatively intact, it could explain the current composition without requiring exotic formation conditions. But the chemical anomalies extend beyond carbon dioxide dominance. Spectral observations from Chile's extremely large telescope revealed another perplexing feature: prominent nickel atomic emission lines, paired with astonishingly faint iron spectral features. This represents a significant deviation from typical solar system composition. In solar system bodies, iron and nickel exist roughly in solar proportions, reflecting the elemental abundance of the protostellar nebula from which they condensed. The apparent depletion of iron relative to nickel in 3I Atlas raises profound questions about its formation environment or subsequent evolution. One speculative possibility involves differential treatment of metallic components. During the object's interstellar journey, iron and nickel possess distinct sublimation temperatures and chemical reactivity. Thus, prolonged exposure to cosmic radiation or interstellar dust impacts may selectively remove iron, while preserving nickel in more stable chemical forms. Another intriguing hypothesis suggests that Comet 3I Atlas may have formed within a stellar environment characterized by non-solar elemental abundances. If its parent star belonged to a distinct galactic population, perhaps the thick disk or halo population, containing stars with anomalous chemical compositions, then the resulting planetary debris would naturally exhibit iron-to-nickel ratios distinct from those observed in our local universe. As summer transitions into autumn, Comet 3I Atlas continues its journey toward its October perihelion. Its tail structure grows increasingly complex and visually spectacular. Observations from the Gemini Observatory and other ground facilities have documented multiple tail components with distinct colorations and apparent granularities. This multi-component structure indicates that volatile reservoirs are being sequentially activated across different regions of the comet nucleus. After billions of years in the cold, empty void of interstellar space, this object truly came to life under the sun's warmth. Polarimetric measurements of the comet analyzed the polarization state of sunlight scattered within the coma and tail, providing additional clues about the nature of dust particles ejected from the nucleus. Polarimetric features suggest the dust particles exhibit unusual size distributions or optical properties compared to typical solar system comets. This may indicate distinct formation processes within the protoplanetary disk, or extensive modification during its long interstellar journey. A particularly intriguing aspect of Comet 3I Atlas involves intermittent brightening events unrelated to its solar distance. Most comets follow predictable brightening curves near perihelion, where brightness steadily increases as heliocentric distance decreases. However, 3I Atlas exhibits periodic, explosive outbursts, suggesting more complex internal processes. These outbursts may occur when solar heating strips away surface crusts, suddenly exposing fresh, volatile-rich material. Many comets form dusty shells, composed of processed organic matter that inhibits sublimation, until thermal stress or gas pressure breaches these protective layers. When breakthrough occurs, underlying pristine ice can rapidly sublimate, causing temporary, dramatic increases in activity. Alternatively, this intermittent behavior may reflect internal structural changes in 3I Atlas as it adapts to solar heating. After billions of years in the cold of interstellar space, temperature gradients penetrating the comet nucleus may trigger subsurface sublimation, disrupting internal ice deposits, exposing fresh surfaces to solar radiation, and generating cascading activation events. The rotational behavior of 3I Atlas also appears anomalous compared to typical solar system comets. Photometric observations designed to measure brightness changes during nuclear rotation either reveal unusually long rotation periods or display complex tumbling motions with indistinguishable periods. This may indicate structural changes during its interstellar journey, or simply reflect its original angular momentum state upon ejection from its parent system. Yet perhaps the most unsettling aspect of 3I Atlas's behavior is how normal it appears in some respects, while being utterly unprecedented in others. The fundamental physics governing coma formation, tail development, and volatilization sublimation follow well-established principles. However, its specific chemical characteristics, temporal evolution, and structural properties seem to defy every expectation based on decades of cometary research. This fusion of familiar and alien traits indicates that 3I Atlas represents a genuinely novel astronomical experience, not merely a comet from another galaxy, but a window into planetary formation processes and stellar environments, fundamentally distinct from our local cosmic neighborhood. This object simultaneously confirms and challenges our understanding of how planetary systems evolve and what kind of debris they eject into the Milky Way. As Comet 3I/Atlas enters its final weeks before perihelion in late October and temporarily vanishes into the sun's glare, accumulating observational evidence paints an object resistant to simple classification. Based on its activity and spectral characteristics, it is unmistakably a comet. Yet its chemical composition and behavioral patterns mismatch any known category of solar system bodies. The question is whether these anomalies reflect genuinely exotic physics and chemistry, or merely represent extreme cases of natural variation in planetary system debris. The answer to this question must wait until December, when 3I Atlas reemerges from its solar hiding place and provides telescopes with the best opportunity for detailed characterization. But even as astronomers prepare for months of intensive observation, another conjecture begins to emerge from the data. For while the peculiar behavior of 3I Atlas might be explained by unusual natural processes, it also raises unsettling questions about whether we are dealing with something more than just an unusual comet originating from another solar system. The anomalous celestial cluster of September 2025 serves as a sobering reminder that our planetary defense capabilities, despite decades of development, remain disturbingly fragile. While we successfully tracked and characterized every significant object approaching Earth during that tumultuous season, the clustering of these encounters highlighted critical vulnerabilities that, if exploited by the wrong visitor at the wrong time, would be catastrophic. The fundamental challenge in monitoring lies first in observational geometry limitations. The vast majority of our asteroid search telescopes are ground-based facilities. They can only observe objects with sufficient angular separation from the sun in the sky. This creates a massive blind spot, the approach path from the direction of the sun. The impactor responsible for the Chelyabinsk event in 2013 arrived completely undetected from this direction. An asteroid approaching from the sun's direction is essentially undetectable until the final hours or even minutes before atmospheric entry. Fortunately, FA-22's orbit avoided this monitoring shadow zone, allowing global telescopes to track its trajectory weeks before closest approach. However, had its orbital inclination differed, or its approach vector aligned more closely with the Sun-Earth line, we might have had only days or even hours of warning, instead of the comfortable lead time that allowed for detailed characterization and public notification. This sunblind zone represents one of the deadliest vulnerabilities in our current planetary defense architecture. Ground-based sky surveys have made remarkable progress in cataloging near-Earth objects, but they remain fundamentally constrained by the laws of optics and orbital mechanics. No matter how advanced your telescope, you cannot observe what lies hidden behind the brightest objects in the sky. The solution lies in deploying monitoring systems into space, enabling them to operate independently free from Earth's day-night cycle and atmospheric interference. NASA's Near-Earth Object Pathfinder mission is scheduled for launch in September 2027. It will deploy a specialized infrared space telescope designed to observe asteroids. This telescope will operate in a position behind Earth in its orbit around the Sun. From this advantageous vantage point, the Pathfinder will detect approaching objects from directions invisible to ground-based observatories. Yet space-based monitoring represents only the first step in the complex chain of planetary defense capabilities. Once a potentially hazardous object is identified, it must undergo sufficiently detailed characterization to assess its actual threat level and determine the most effective response strategy. This requires rapid follow-up observations from multiple facilities, precise orbital determination, and detailed analysis of the object's physical properties. The Vera C. Rubin Observatory achieved first light in June 2025, representing a revolutionary advancement in this follow-up capability. Its massive mirror and wide-angle camera can rescan the entire observable sky every 3 nights, providing unprecedented temporal resolution for tracking newly discovered objects and monitoring their orbital evolution. Within its first 10 hours of operation, the Rubin Observatory captured thousands of new asteroid detections, demonstrating the instrument's potential to vastly expand our census of the near-Earth object population. However, monitoring and tracking would be meaningless without the practical capability to counter incoming threats. This is precisely where NASA's Double Asteroid Redirection Test, DART, mission provides invaluable real-world validation. The DART spacecraft impacted the asteroid Dimorphos on September 26, 2022, successfully shortening the smaller satellite's orbital period by 32 minutes, far exceeding the minimum 4-minute change required to confirm mission success. More significantly, detailed impact analysis indicates a momentum transfer efficiency of approximately 3.6, meaning the deflection effect achieved was nearly 4 times greater than predicted by simple momentum conservation. This amplification stems from the ejection of debris following impact, which acts like rocket exhaust to magnify the deflection effect. Understanding this physical mechanism is crucial for designing future deflection missions. ESA's Hera mission is currently en route to the Dimorphos system. It will arrive in 2026 to conduct forensic analysis of the DART impact site. Hera's detailed mapping and measurement of the crater and debris field will provide ground truth data for impact models, helping refine our understanding of how different asteroid types respond to kinetic impact attempts. However, kinetic impacts represent only one tool in the planetary defense toolkit. For larger celestial bodies or scenarios requiring more precise trajectory alterations, other technologies may prove more effective. Gravity tractors utilize a spacecraft's gravitational field to gently drag asteroids off their original orbits. They can accumulate velocity changes of millimeters per second over years or decades. Nuclear explosive devices can generate powerful rocket-like thrust by vaporizing surface material. Ion beam deflectors can gradually ablate one side of an asteroid using focused particle beams, producing sustained low-level long-term thrust. A key insight in planetary defense research is that all these technologies require substantial lead time to be effective. Applying a slight thrust years or decades in advance eliminates the need for desperate last-minute measures. This is why early detection is so crucial, not because we might need time to evacuate cities or build underground shelters, but because advance warning makes minor deflections exponentially easier to implement. The International Asteroid Warning Network was established to coordinate responses to potential impact threats. During FA-22's approach, activities equivalent to a live-fire exercise were conducted. This asteroid briefly appeared on the European Space Agency's risk assessment list. It was subsequently removed after further observation. This provided valuable experience in navigating the delicate balance between public notification and panic prevention. How do you inform the world about an asteroid threat without causing economic disruption or social unrest? How do you coordinate international responses when dealing with celestial bodies that could impact multiple nations? These questions have no simple answers. Yet FA-22's flyby offered a relatively low-risk opportunity to test communication protocols and decision-making processes. This exercise revealed both strengths and weaknesses in our current approach. Rapid international sharing of observational data enabled swift refinement of FA-22's orbit and prompt removal from the risk assessment list after the threat was ruled out. However, public communication remained inconsistent. Some media outlets sensationalized initial risk assessments, while others ignored the story entirely until the safe flyby was confirmed. Part of the communication challenge stems from inherent uncertainties in early orbit determination. When an asteroid is first detected, its trajectory constraints are poor due to limited observational data. The uncertainty region, the range of possible orbits consistent with existing measurements, may simultaneously include both impact and miss scenarios. Only additional observations can reduce this uncertainty until definitive predictions become possible. This creates a fundamental tension in planetary defense communications. Waiting until the impact probability drops to zero could mean losing valuable preparation time if the object is actually on a collision course. But releasing information while significant uncertainty remains could trigger unnecessary panic, or, worse, lead to public distrust if threat assessments later change. September's cluster also highlights persistent gaps in our detection capabilities. Long-period comets from the outer solar system can still appear with relatively short warning times, because their highly elliptical orbits keep them in distant, undetectable regions for most of their cycles. For example, Comet Swift-Tuttle, with an estimated nucleus diameter of 26 kilometers, is large enough to cause global devastation if its orbit intersected Earth's path, but its next return isn't until 2026. Perhaps most concerning are city-killer-sized objects, ranging from 100 to 300 meters in diameter, large enough to cause regional devastation, yet too small to detect until extremely close. Current surveys have cataloged most kilometer-scale objects capable of global impact, but the inventory of smaller potentially hazardous asteroids remains incomplete. The September event also raises unsettling questions about our capacity to handle multiple simultaneous threats. While FA-22 dominated headlines, dozens of smaller objects traversed our cosmic neighborhood concurrently. If several city-killer-sized asteroids approached from different directions at once, would our tracking and characterization capabilities become overwhelmed? Could we launch deflection missions targeting multiple objects using current technology and resources? These scenarios remain hypothetical, yet underscore the critical importance of sustained investment in planetary defense infrastructure. The completion of the Vera C. Rubin Observatory's Sky Survey, the deployment of the Near-Earth Object Survey, and ongoing advancements in deflection technologies represent pivotal steps toward a truly robust planetary defense capability. But they are merely the beginning. Protecting human civilization from cosmic impacts will require multi-generational effort. The good news is that planetary defense is fundamentally solvable. Unlike earthquakes, volcanic eruptions, or other natural disasters, asteroid impacts are entirely preventable, with sufficient warning and appropriate technology. The physics of deflection is clear and understandable. The necessary technology is within our capabilities. The framework for international cooperation already exists. What we need now is the political will to maintain funding and support for these systems. During the long intervals between major impact threats, planetary defense is like insurance. It always seems unnecessary until you desperately need it. September's cluster serves as a valuable reminder. We inhabit an active cosmic environment. Impact is not a question of if, but a question of when. Yet as astronomers labored to catalog and describe that eventful autumn, during the parade of near-Earth objects passing by our planet, another mysterious phenomenon began emerging from observational data. The timing of encounters, the clustering of trajectories, and the interstellar visitors, arriving within the same narrow time window, began to challenge the limits of statistical probability. Were we witnessing a highly improbable convergence of unrelated events, or some more fundamental force orchestrating this cosmic dance? In the age of social media and viral conspiracy theories, it was perhaps inevitable that 3I Atlas would eventually face the question that has haunted every unusual astronomical discovery since the dawn of the space age. Could this be evidence of extraterrestrial intelligence? The object's unprecedented chemical composition, complex behavior, and remarkably convenient timing for observation kept conspiracy theorists working overtime. By late September 2025, academic speculation began rather innocently. Researchers noted similarities between Oumuamua and the controversial interstellar object Oumuamua, sparking debates about possible artificial origins. Both were interstellar visitors. Both exhibited unusual characteristics, challenging conventional understanding. Both possessed orbits offering exceptional observational opportunities for human astronomers. But the similarities end there. The differences are profound and compelling. Unlike Oumuamua's enigmatic cigar shape and lack of visible outgassing, coupled with its mysterious non-gravitational acceleration, 3I Atlas behaves and appears exactly as a comet should. As it approached the Sun, it formed a classic coma and tail structure. Its brightness variations, based on volatile sublimation, followed a predictable pattern. Its trajectory exhibits the expected gravitational bend from solar interaction. Additional perturbations are readily explained by the force of gas release. Most crucially, 3I Atlas shows no signs of controlled or directed motion. Its path through the solar system follows a precise hyperbolic trajectory. This is precisely what one would expect from an unbound visitor influenced solely by the sun's gravity. No course corrections, no unexplained accelerations, no radio transmissions, no geometric or man-made structures, not even at the highest resolution telescopes available to humanity. The scientific method demands that extraordinary claims require extraordinary evidence. And the evidence for 3I Atlas consistently points to natural phenomena. Though natural phenomena unlike any previously observed among our cosmic neighbors. Every peculiar behavior, every unusual chemical feature, every anomalous physical property has a reasonable explanation grounded in established physics and chemistry. Consider the extreme carbon dioxide dominance that makes the 3 Atlas's chemistry so extraordinary. While unprecedented in solar system comets, such composition readily forms in the outer regions of an unusual planetary system, with differing stellar mass, metallicity, or planetary architecture. Chemical features peculiar to observers familiar only with products of our local solar system may naturally arise in such environments. The apparent iron depletion relative to nickel, while puzzling, may reflect formation within a stellar environment possessing non-solar elemental ratios, or subsequent processing during billions of years of interstellar travel. Cosmic ray bombardment of interstellar dust impacts and deep space thermal cycling may have selectively altered surface composition, producing unusual spectral features without any intelligent intervention. Even complex multi-component tail structures and intermittent brightening events have precedence in solar system comets, though their observed behavior undeniably reached extremes. Comet Holmes underwent a dramatic outburst in 2007, increasing in brightness nearly a millionfold. Natural processes clearly capable of producing the spectacular and unusual behavior. observed in 3I Atlas. The real question is not whether 3I Atlas might be artificial, but why people persistently ask this question. Part of the answer lies in contemplating the psychological impact of true interstellar scale. When we observe objects from other stellar systems, we confront the possibility of intelligent existence elsewhere in the Milky Way. The human brain evolved to navigate social hierarchies and detect agency in complex environments, naturally seeking signs of purpose or intent in unexplained phenomena. This tendency intensifies when confronted with objects that seem to defy our expectations or exhibit properties beyond conventional explanation. The peculiar chemistry and convenient observational geometry of 3I Atlas triggered the same pattern recognition systems our ancestors used to identify potential predators or allies when facing unprecedented phenomena. The brain's default assumption is often that someone or something must be responsible. Yet nature routinely produces phenomena beyond human imagination. The universe has conducted 13.8 billion years of physical and chemical experiments, under conditions ranging from the interiors of massive stars to interstellar space near absolute zero. In truth, our occasional encounters with surprising natural processes or objects are not evidence of artificial origins, but proof that our understanding of cosmic phenomena remains fundamentally incomplete. The media environment surrounding astronomical discoveries also tends to amplify speculation about artificial origins. Headlines like "Scientists Baffled by Mysterious Interstellar Visitors" generate more clicks than reports of researchers studying unusual but natural comets. Regardless of which headline more accurately reflects scientific consensus, this creates a feedback loop. Public interest drives sensational reporting, which in turn fuels more speculation about exotic explanations. Social media accelerates this effect by allowing unscreened speculation to spread faster than cautious scientific analysis. By the time astronomers gather sufficient data to characterize a celestial object and rule out artificial origins, alternative theories have already reached viral status and developed resistance to correction through factual information. The historical pattern is clear and consistent. Every unusual astronomical discovery, from pulsars to fast radio bursts, initially faces speculation about possible artificial origins. In each case, sustained observation and analysis reveal natural explanations that, while often more complex and fascinating than initially anticipated, require no involvement of extraterrestrial intelligence. This does not mean we should abandon the search for evidence of extraterrestrial technology. The universe almost certainly contains other intelligent civilizations. Some may possess the capability for interstellar travel or communication, but detecting these civilizations will require unambiguous evidence of artificial origin. Coherent radio signals carrying informational content, objects exhibiting controlled motion inconsistent with natural forces, or structures violating the laws of physics as we understand them. 3I Atlas exhibits none of these characteristics. Its radio emissions consist entirely of natural thermal radiation and molecular spectral lines typical of gas released by comets. Its trajectory follows predictable gravitational mechanics. Volatile material supplements, easily explaining perturbations. Its internal structure, as revealed by thermal models and photometric observations, consists of a loose aggregate of ice and rock held together by weak gravitational and cohesive forces. Perhaps most compellingly, 3I Atlas behaves exactly as we would expect from planetary formation debris originating from another star. Theoretical models predict that during formation and early evolution, each stellar system should eject vast quantities of small bodies. These objects would drift through interstellar space for millions or billions of years, occasionally encountering other stellar systems where they might be observed as interstellar visitors. The chemical and physical properties of such bodies should reflect the conditions of their parent systems. Different stellar masses, different elemental abundances, different planetary configurations, different thermal histories. A genuine sample of debris from another star system should appear alien compared to solar system bodies, while still obeying the same fundamental physical and chemical laws governing matter throughout the universe. In other words, 3I Atlas appears exactly as it claims to be, a natural product formed within a planetary system orbiting another star, bearing chemical signatures reflecting its formation conditions, conditions distinct from those that produced our local solar family. Its strangeness to human observers is not evidence of artificial origin, but confirmation that we inhabit a galaxy where planetary formation conditions vary from system to system. As 3I Atlas continues its approach toward perihelion in late October, the accumulating evidence consistently supports a natural explanation for its peculiar characteristics. Yet this raises a more compelling question than whether it might be artificial. Where exactly did this ancient wanderer spend the billions of years between ejection from its birth star system and its recent arrival in our cosmic neighborhood? Answering this will require complex galactic dynamics modeling and stellar motion spanning geological timescales. Yet preliminary attempts to trace 3I Atlas's journey through space and time have yielded tantalizing clues about this object's origin and the extraordinary voyage that brought it before our telescopes. Reconstructing the biography of an interstellar visitor means piecing together a journey potentially older than Earth itself. Within 3I Atlas's chemical signature and orbital path lies a fossil record of cosmic events from billions of years ago, when our galaxy was still young, and the distribution of stars and abundance of heavy elements were vastly different from today's patterns. The first clues to this object's ancient origins came from kinematic analysis, mathematical modeling conducted by European Southern Observatory researchers attempted to trace its motion through space and time in reverse. Preliminary calculations indicate that 3I Atlas may originate from the galactic thick disk stellar population. These stars formed during the early evolutionary stages of the Milky Way, between 7 and 12 billion years ago. If these kinematic models prove correct, then 3I Atlas would predate our entire solar system. It would have been roaming interstellar space long before the Sun coalesced from its parent molecular cloud, carrying a sample from an era of the Milky Way when star formation rates were higher, and heavy element abundances differed significantly from present-day values. The thick disk hypothesis finds support in the object's unusual chemical signature. Stars within this ancient stellar population typically exhibit distinct elemental abundance patterns, especially when compared to the solar-type stars belonging to the younger thin disk population. The pronounced iron depletion and extreme carbon dioxide content observed in 3I Atlas may reflect formation processes around thick disk stars possessing non-solar metallicity and unusual volatile chemical signatures. But how did such a small object escape its parent star system and embark on its long journey through interstellar space? Ejection processes typically involve gravitational interactions with giant planets. During the chaotic early stages of planetary system evolution, giant planets migrate inward or outward due to interactions with protoplanetary disk material. They can scatter smaller bodies onto hyperbolic orbits, expelling them entirely from the system. Computer simulations indicate that each planetary system ejects significant debris during its formation. For every kilogram of asteroidal and cometary material ultimately gravitationally bound to a planet, roughly 10 kilograms are flung into interstellar space by the gravitational slingshot effect. This implies the Milky Way should be teeming with trillions of wandering fragments from billions of stellar nurseries. Once ejected from its parent system, 3I Atlas embarked on a solitary odyssey through the near vacuum of interstellar space, where the typical density of interstellar matter is roughly 1 atom per cubic centimeter, far exceeding the vacuum achievable in any terrestrial laboratory. In this environment, the object remains largely isolated from external influences, preserved in cosmic cold just a few degrees above absolute zero. Yet this interstellar voyage was not without turbulence. Recent modeling by galactic dynamics experts has identified several close encounters with other star systems during 3I Atlas's long journey. In the past 10 million years alone, the object appears to have passed within approximately 3 light-years of at least 6 distinct stars. Each encounter likely altered its trajectory through subtle gravitational perturbations. The most significant of these stellar encounters occurred roughly 4 million years ago, when 3I Atlas passed within 1 light-year of a red dwarf in Cassiopeia. The gravitational influence from this close encounter was measurable and likely altered the object's trajectory, explaining why its current motion does not point toward any obvious parent system within the Milky Way's thick disk stellar population. This raises intriguing questions about the object's surface evolution. During its interstellar voyage, millions or billions of years of cosmic ray bombardment may have gradually altered exposed ice and rock surfaces through spallation and nuclear fission reactions. High-energy particles from distant supernovae and other galactic phenomena break chemical bonds, produce unusual isotope ratios, and may generate entirely new molecular species absent in typical solar system material. The extremely low temperatures of interstellar space, typically around 3 kelvins, can preserve most volatile substances in solid form throughout the journey. However, periodic encounters with interstellar dust clouds or radiation fields from nearby stars may trigger periodic heating events, causing surface material to sublimate and redeposit in different configurations. This could potentially explain some of the unusual chemical signatures observed by modern telescopes. Perhaps most strikingly, 3I Atlas maintained structural integrity throughout its billion-year journey, despite enduring thermal cycling, cosmic ray bombardment, and occasional interstellar dust impacts. This suggests it either possesses exceptionally robust structure or continuously self-repairs through sublimation and redeposition processes, gradually healing micrometeorite damage and radiation-induced structural changes. The arrival of this object in our solar system represents the culmination of its journey. This is almost beyond human comprehension. Consider the navigational precision required for 3I Atlas to arrive at the right time and orbit for optimal observation by 21st century human telescopes. This object must have survived billions of years in the harsh environment of interstellar space, navigating the gravitational influences of dozens of stellar encounters, and arrive precisely during humanity's brief historical window of technological capability to identify and study it. The timing is unbelievably perfect. 3I Atlas approaches perihelion just as our most advanced space telescopes become fully operational, and our understanding of interstellar chemistry matures sufficiently to appreciate its significance. Centuries ago, it might have been dismissed as just another faint star. Centuries later, it might have been detected but inadequately characterized, before vanishing into cosmic obscurity. The biography of 3I Atlas also illuminates a grander narrative about galactic evolution and the cosmic cycle of planetary matter. Every heavy element in this object's composition was forged in the nuclear furnaces of ancient stars and dispersed throughout space by supernova explosions. The carbon, oxygen, silicon, and trace metals forming its structure, representing the stellar alchemy accumulated through countless generations of stellar births and deaths before the solar system's existence. In a very real sense, 3I Atlas is a messenger from ancient galaxies, carrying samples of planetary formation processes that occurred under conditions vastly different from those that created Earth and its celestial companions. The chemical composition of this object provides clues about how volatile substances condense and evolve within stellar environments possessing distinct metallicity and dynamical histories. The chemical composition of this object provides clues about how volatiles condensed and evolved within stellar environments, possessing differing metallicities and dynamical histories. Yet perhaps the most profound aspect of 3I Atlas's biography lies in the insights it reveals about the interconnectedness of galactic-scale processes. This object originated as part of a planetary disk forming around another star, potentially located in a completely different region of the Milky Way. Through a complex chain of gravitational interactions, stellar motions, and cosmic coincidences, it ultimately entered our telescopes, carrying information about its origins across vast distances and timescales. If confirmed, the thick disk origin hypothesis would make 3I Atlas a fossil from the Milky Way's youth, when stellar formation activity was more vigorous, and the chemical composition of interstellar space differed significantly from present-day values. Studying this ancient wanderer could provide insights into the chemical evolution of the Milky Way, early planet formation processes, and the distribution of volatiles in primordial galaxies. Yet despite all the complex modeling and chemical analysis, fundamental questions about the 3I Atlas system's origin remain unanswered. We cannot identify its parent star or the planetary system where it formed. Gravitational chaos in galactic evolution has erased most traces of its original trajectory, only leaving statistical hints about its possible thick disk origin. This uncertainty reflects the inherent challenges of interstellar archaeology. Unlike terrestrial fossils still embedded in measurable strata, cosmic travelers like 3I Atlas lack direct evidence of their origins, time, or place. Their stories must be reconstructed through indirect clues, chemical composition, isotope ratio trajectories, and statistical models of galactic dynamics. Yet these limitations do not diminish the significance represented by 3I Atlas. Even without knowing its precise birthplace, we can be certain it carries an authentic sample from another world, one formed under conditions distinct from our own solar system. Each spectral observation and chemical analysis yields new data on the diversity of planetary formation processes and the range of environments in which worlds emerge around other stars. As 3I Atlas continues its final phase toward perihelion in late October, astronomers prepare for its temporary disappearance behind the sun's glare. The weeks surrounding perihelion should be the most scientifically valuable phase of the entire encounter. Maximum solar heating will drive peak levels of volatile outgassing and potentially expose subsurface material preserved for billions of years since the body's formation. Yet the same solar radiation that promises to reveal 3I Atlas' deepest secrets will also erase it from Earth's view. Its trajectory brings it within 0.4 astronomical units of the Sun, approximately 60 million kilometers, closer than Mercury's average orbital distance. From Earth's perspective, this places 3I Atlas within 10 degrees of the solar disk, buried in twilight, rendering precise astronomical observation impossible. This forced observational hiatus creates an intriguing puzzle. Will 3I Atlas reappear intact as a coherent single body in December, upon its December reappearance, accompanied by heightened activity fueled by newly exposed volatiles? Or will thermal stresses disrupt its internal structure, splintering it into multiple fragments, forming an extended debris cloud visible as distinct cometary bodies? The implications of survival extend far beyond academic curiosity. Intact survival would demonstrate interstellar objects possess sufficient structural integrity to preserve ancient chemical signatures even under intense solar heating, while fragmentation, may offer spectacular spectral views. It risks transforming 3I Atlas, a scientifically valuable pristine sample from another star system, into a processed stream of debris. Historical precedents offer scant guidance. Most solar system comets that fragment near the Sun are new visitors from the Oort cloud experiencing their first intense solar radiation. By contrast, 3I Atlas is a battle-hardened survivor, having demonstrated extraordinary structural stability throughout its billion-year interstellar journey. The cosmic irony is palpable. After traversing unimaginable space-time distances to reach our solar system, 3I Atlas will undergo its most active and illuminating phase, hidden behind the star that enabled its remarkable transformation. Much like attending a concert only for the lead performer to vanish behind the curtain during the most crucial song. Yet astronomical patience yields its rewards. Earth's orbital motion around the Sun will gradually improve the observational geometry for objects near our star. By early December, 3I Atlas will begin emerging from the Sun's glare into prime viewing position. The object's closest approach to Earth is anticipated around mid-December, at a distance of approximately 18 astronomical units, roughly 2.7 billion kilometers. By Earth standards, this seems distant, yet it represents optimal conditions for detailed spectral analysis. Close enough for large telescopes to gather substantial light, yet distant enough to avoid atmospheric interference and Earth's own thermal radiation. Positioned in the pre-dawn sky where background contamination is minimal, December's observation window likely represents humanity's best opportunity, for decades, perhaps centuries, to study intact interstellar material. Unlike 1I Oumuamua's fleeting visit and swift departure, 3I Atlas's trajectory and timing will keep it within the observational reach of major observatories. Until 2026, providing months of continuous observation across multiple wavelengths. However, before we can assess these broader implications, the object must survive its closest encounter with the Sun and reappear. Its behavior during perihelion will yield critical data on interstellar comet survival and the preservation of ancient chemical signatures under extreme thermal processing. The stakes extend beyond pure scientific curiosity. Should 3I Atlas disintegrate during perihelion, we may lose the opportunity for a comprehensive study of this interstellar material, until another such visitor arrives decades or centuries hence, with favorable observational geometry. Yet if it survives its December reappearance, it may yield the most detailed description of extrasolar matter ever obtained by human science. The human brain is meticulously evolved to detect patterns, even where none exist. This evolutionary adaptation helped our ancestors spot predators in tall grass and recognize seasonal shifts between feast and famine. Yet against the backdrop of astronomical phenomena, the same pattern recognition system may mislead us to seek connections and conspiracies amid cosmic random noise. However, sometimes patterns are real. Consider Asteroid 2025 FA22, which on September 20th swooped past Earth at 22 lunar distances. 3 days prior, the smaller body 2025 RJ2 passed by at just 0.78 lunar distances. That same week, multiple additional near-Earth objects traversed our local cosmic space. Each was cataloged and tracked by the Global Monitoring Network. Comet C 2025 R2 Cygni brightened to naked-eye visibility in the night sky. Lurking in the background, interstellar visitor 3I Atlas approached its October perihelion. After a journey spanning billions of years, individually, none of these events is particularly remarkable. Dozens of asteroids pass within 1 astronomical unit of Earth each month. Following orbital mechanics established billions of years ago, comets periodically brighten and dim as they orbit closer to and farther from the Sun. Interstellar objects, though rare, are expected consequences of planetary formation and evolution around other stars. Yet, these events clustering within such a narrow time window begins to challenge simplistic explanations based on cosmic coincidence, interstellar visitors, and unusual near-Earth object activity cycles. What are the odds of their arrival in the same month? What is the probability that a newly discovered comet reaches peak visibility, just as multiple asteroids approach? One intriguing speculative thread involves the possibility of gravitational shepherding, that 3I Atlas's passage through the inner solar system might somehow alter the trajectories of smaller bodies. The gravity of a large object can disrupt smaller asteroids' orbits, potentially triggering an avalanche or entourage effect. This might explain September's cluster of encounters. However, physicists strongly object to this scenario, even at its maximum estimated size of approximately 6,000 meters. 3I Atlas lacks sufficient mass to exert significant gravitational influence. On other bodies at distances of millions of kilometers. Newton's inverse square law implies gravitational effects diminish rapidly with distance and become negligible at the scale of the September encounters. Furthermore, the orbital elements of different September visitors show no evidence of a common origin or shared dynamical history. FA-22 follows a typical near-Earth object orbit with moderate eccentricity and inclination. The smaller asteroids detected throughout the month exhibit the full range of orbital characteristics expected from the background population of near-Earth objects. No evidence indicates hyperbolic trajectories, suggesting recent gravitational interactions with interstellar intruders. A more plausible explanation for the apparent clustering involves observational bias and detection timing effects. The Vera C. Rubin Observatory achieved first light in June 2025, dramatically expanding our ability to detect and track small near-Earth objects. Improved sky coverage naturally yields more discoveries, creating the impression of heightened activity even if the underlying population remains unchanged. This can be likened to suddenly installing high-definition security cameras in previously unmonitored areas. The number of people passing through that space hasn't changed, but your awareness of their presence increases dramatically. Similarly, enhanced astronomical measurements reveal the true density of near-Earth objects. These bodies have always been there, but went undetected by less sensitive instruments. The psychological phenomenon of illusory perception, the tendency to perceive meaningful patterns in random information, may also influence our interpretation of the September events. Once the initial close approaches were reported, both astronomers and the public became more attuned to subsequent discoveries. Objects that might have gone unnoticed during a quiet news cycle suddenly garnered front-page attention, creating a feedback loop that amplified perceptions of anomalous activity, yet even accounting for observational bias and psychological effects. Certain aspects of the September cluster defy explanation by purely random processes. 3I Atlas was discovered in July with its trajectory precisely timed to achieve maximum visibility during the peak of near-Earth object activity, representing a startling coincidence that challenges the limits of statistical probability. Consider an alternative speculative scenario. 3I Atlas is not a single isolated object, but the largest member of a larger interstellar material cluster. If the original parent body fractured during its long space journey, possibly due to internal stresses or collisions with interstellar dust, the resulting debris stream could span vast spatial regions. In this context, the September asteroid encounters may represent smaller fragments of the same primordial body, following slightly divergent trajectories that brought them near Earth at staggered times. The fragments would retain interstellar velocity characteristics, but could have been temporarily captured into solar orbits during prior transits through the inner solar system. However, this fragmentation hypothesis faces significant observational challenges. Spectral analysis of the September asteroids reveals typical carbonaceous or silicate compositions consistent with solar system origin. Available reflectance spectra match known asteroid classification categories, rather than the unusual chemical signature exhibited by 3I Atlas. If these bodies share an interstellar origin, we would expect to observe similar chemical signatures across the entire population. Furthermore, orbital dynamics do not support a common origin scenario. True interstellar fragments would exhibit hyperbolic orbits similar to 3I Atlas itself, rather than the elliptical orbits characteristic of gravitationally bound solar system bodies. Capturing interstellar debris into stable near-Earth orbits through planetary gravitational interactions requires energy inputs exceeding available resources. Perhaps the most mundane explanation is also the most probable. We are witnessing the statistical equivalent of multiple lightning strikes. Unlikely individual events occasionally cluster together by sheer coincidence. The cosmos owes no obligation to distribute cosmic encounters uniformly across human timescales. Random processes can and do produce seemingly meaningful apparent patterns. The rapid expansion of investigative capabilities in the 2020s means we are observing this cosmic neighbor with unprecedented sensitivity and cadence. Previous generations of astronomers might have entirely missed most September encounters, or detected them as isolated events spanning different news cycles. Our current ability to simultaneously discover, track, and characterize multiple near-Earth objects creates opportunities for apparent clustering that simply did not exist in the early history of astronomical observation, despite rational analysis pointing to coincidence and observational bias. 3I Atlas's precise arrival coincides with heightened NEA activity, coupled with its unprecedented chemical signature and ancient origin, suggesting we may witness something more significant than random convergence of unrelated events. Answers may only emerge after months of detailed study of 3I Atlas. Following its December reappearance from solar glare, detailed spectral analysis, precise ballistic measurements, and careful comparisons with the September asteroid population may reveal connections not apparent in initial observations. But if such connections fail to emerge, if 3I Atlas proves truly isolated from the September encounter, then we face a more intriguing possibility. Perhaps the cosmos is simply more active and interconnected than our Earth-centric perspective typically allows us to appreciate. Perhaps this seemingly extraordinary convergence is actually normal on a galactic scale. The question is not whether something is following 3I Atlas, but whether we have finally developed the observational capabilities to perceive the true complexity of the cosmic environment we have always inhabited. If so, then the September cluster may merely mark the beginning of our education as galactic citizens. In a galaxy where 400 billion stars constantly exchange matter across vast interstellar space, the ultimate cosmic dramas often unfold in silence. For 3I Atlas, concealed behind the sun's blinding glare, the climax of its journey is destined to be a solitary ritual, unwitnessed by any ground-based telescope. On October 30th, 2025, when this ancient wanderer reaches perihelion, the global astronomical community will gaze into the void, awaiting indirect signals relayed from the sun's far side. Coronal observation satellites recorded subtle disturbances in solar wind parameters, while Deep Space Network antennas strained to detect radio bursts potentially triggered by the comet's evaporating material. All this felt like guessing the content of a grand performance through a thick curtain. Science, in this moment, seemed both meticulous and powerless. During the week's Atlas 3, I remained hidden behind the sun's glare. Observatories worldwide remained active. They redirected their observational efforts toward other performers in this cosmic symphony. Comet C/2025 R2, C/2025 R2 Cygni, bravely faced its perihelion test in early November and unexpectedly maintained its structural integrity when it reappeared in the pre-dawn sky mid-November. Its tail stretched to an astonishing 20 degrees, becoming a magnificent spectacle visible to the naked eye in light pollution-free regions, sparking a global surge of amateur observations. The comet's resilience offers another invaluable case study for researching cometary nucleus structure and volatile components. Meanwhile, routine operations of the Planetary Defense Network continue unabated. The full operational deployment of the Vera C. Rubin Observatory has elevated the discovery rate of near-Earth objects by an entire order of magnitude. Smaller bodies previously overlooked are now integrated into a sophisticated monitoring network. This surge isn't due to the solar system suddenly becoming crowded, but rather because we finally possess the visual capabilities to perceive the true state of our cosmic environment. The anomalous cluster of September 2025 gradually revealed its true nature under this new observational scale. It may not be a statistical anomaly, but rather the first genuine manifestation of the normal distribution of material within the inner solar system. The critical moment in early December finally arrived. Over a dozen major observatories worldwide aimed their most powerful instruments at the calculated region where 3I Atlas was expected to reappear. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and the James Webb Space Telescope, still orbiting, all entered a state of heightened alert. The initial signal came from an observatory in South Africa. Before dawn on December 4th, they captured that familiar point of light. Immediately, observatories worldwide confirmed. Not only had 3I Atlas survived, its brightness had increased by several magnitudes compared to before its disappearance. The ensuing weeks became a golden era in interstellar celestial research. Spectral analysis revealed that after intense solar heating, 3I Atlas retained its unique cosmic signature in chemical composition. Extreme carbon dioxide ratios and iron-nickel anomalies persisted, yet new molecular spectral lines detected near perihelion indicated deeper internal material had been activated and exposed. These new data imposed more precise constraints on the formation environment of its parent star system. The most exciting discovery came from detailed analysis of its dust particles. High-resolution imaging revealed microscopic silicate globules and carbon-rich particles within Comet 3I/Atlas's coma. Their structure and composition markedly differ from similar materials in solar system comets. These interstellar dust grains act as time capsules encapsulated in ice, preserving direct evidence of planetary formation processes in another star system billions of years ago. By the time 3I Atlas reached its closest approach to Earth in mid-December, it had already delivered more data to the scientific community than all previous interstellar visitors combined. This wave of observations will continue through early 2026, as the object gradually recedes and its brightness slowly fades. Yet monitoring persists to track its evolution during departure from the inner solar system. The impact of this series of events extends far beyond academic research. The global public closely followed this cosmic drama through media and online platforms. 3I Atlas's journey became an unprecedented science outreach event, igniting a new generation's interest in space exploration. More significantly, this event spurred the international community to accelerate investment and development in planetary defense systems. Between 2026 and 2028, building on the experience gained in 2025, entered a phase of rapid advancement. NASA's ENIO Surveyor mission launched as scheduled and promptly began scanning the sunward blind zone from the Sun-Earth L1 point. The European Space Agency approved follow-up plans for the Hera mission, aimed at testing more advanced asteroid deflection technologies. The multinational International Asteroid Warning Network established standardized protocols for threat assessment and information sharing. Research on interstellar objects also entered a new phase. Astronomers began re-examining past sky survey data to identify potentially overlooked interstellar visitors. Theoretical models were adjusted accordingly, predicting the occurrence rate of such objects could be an order of magnitude higher than previously thought. Our solar system may be continuously bathed in debris showers from different stellar systems, only now possessing the capability to detect them. Within its first year of full operation, the Vera C. Rubin Observatory discovered 2 additional objects with faint hyperbolic orbits, though significantly smaller than 3I Atlas, and lacking pronounced cometary activity. Their detection confirms that the continuous influx of interstellar matter is not a rare phenomenon. We stand at the threshold of a new era in interstellar astrophysics. With ongoing advancements in observational technology and deepening global collaboration, human understanding of our near-solar environment is undergoing a fundamental shift. We no longer view asteroids and comets as isolated objects, but recognize them as integral components of a complex solar system ecosystem, engaged in ongoing material exchange with the galactic environment. The anomalous cluster of 2025 and the arrival of 3I Atlas ultimately proved not cosmic anomalies, but true reflections of our cosmic neighbors, a universe far more dynamic, interconnected, and full of surprises than we had previously imagined. When we look back on that extraordinary autumn of 2025, recalling the vigilance sparked by asteroid FA-22's close flyby, Comet Cygnus's magnificent display across the night sky, and the profound insights brought by interstellar visitor 3I Atlas, this chain of events was not merely a record of astronomical phenomena, but a fundamental shift in humanity's cosmic perspective. Before that autumn, we tended to view the solar system as a relatively closed system, where planets followed stable orbits for billions of years, and asteroids and comets adhered to predictable paths. Occasional close encounters were seen as statistical anomalies, while visitors from other star systems were once-in-a-millennium spectacles. This perspective stemmed from our limited observational capabilities and brief historical vantage point, from the wishful imposition of human timescales upon cosmic processes. The multiple astronomical events of 2025 shattered this comfortable understanding. We witnessed how crowded the inner solar system could become, observed tangible evidence of matter pouring in from interstellar space, and recognized we inhabit a dynamic, interconnected cosmic environment. This paradigm shift rivals Copernicus's removal of Earth from the cosmic center, or the revolutionary impact of Hubble's discovery of galaxy recession. We now recognize not only that Earth is an ordinary planet orbiting an ordinary star, but also that this star itself is immersed in the Milky Way's material currents, constantly receiving messengers from across the cosmos. The journey of 3I Atlas holds profound symbolic significance. This ancient object, having journeyed through interstellar space for billions of years, carries the memory of another world, bearing the chemical signatures of diverse planetary formation environments. Its arrival is not accidental, but a natural outcome of the Milky Way's material cycle. Just as Earth's water may partly originate from cometary delivery, all heavy elements in our solar system trace back to the explosions of previous stars. The Milky Way itself is an ecosystem, bound by gravity and sustained by material exchange. From the perspective of planetary defense, the 2025 event serves both as a guide and a wake-up call. The guidance lies in our witnessing the effectiveness of global monitoring networks and international cooperation mechanisms in addressing potential threats. The wake-up call is our forced acknowledgement that existing capabilities still falls significantly short of the comprehensive protection required. That autumn taught us that warning time, international cooperation, and technological preparedness are the three indispensable pillars for confronting cosmic risks. The absence of any one element could lead to catastrophic consequences. Yet deeper than the technical challenges lies a philosophical revelation. The existence of 3I Atlas and other interstellar bodies reminds us that planetary formation processes are both universal and diverse across the Milky Way. The cosmos teems with material samples from worlds we cannot yet imagine. These worlds may possess chemical compositions and physical environments vastly different from Earth's. Their existence expands the boundaries of our understanding of habitability and the potential for life. When we scrutinize the spectral data of 3I Atlas, we are not merely analyzing the chemical composition of an extraterrestrial object, but reading a cosmic epic spanning interstellar distances and geological time. This epic chronicles the birth and death of stars, the cycle of matter, and the formation and dissolution of planetary systems. Within this grand narrative, humanity is both reader and participant. Our science, our technology, our contemplation of our place in the cosmos all become new chapters in this story. Viewing the 2025 astronomical events from a broader perspective marks a pivotal turning point in human civilization's development. We are transitioning from a single-planet species to an interstellar civilization conscious of its cosmic environment. This transition demands not only technological advancement, but also a shift in our cognitive framework. We must learn to think on a galactic scale, plan across eons of time, and act with reverence for the universe's complexity. As the 3I Atlas continues its journey toward the outer solar system and eventually re-enters interstellar space, carrying data about humanity and human science, it becomes a two-way messenger, delivering information from distant star systems to us, while carrying evidence of Earth's civilization outward. In the endless cosmic darkness, such connections hold profound significance. Looking ahead, as more powerful telescopes come online and space missions reach ever-distant destinations, we will undoubtedly discover celestial bodies and phenomena that challenge our understanding. Follow-up observations from the Vera C. Rubin Observatory may reveal the prevalence of interstellar visitors far exceeds expectations. Probes to Europa and Enceladus could uncover the first evidence of extraterrestrial life. Studies of exoplanet atmospheres might identify potential biosignatures. Yet amid all these future discoveries, the lessons of 2025 will resonate enduringly. They remind us that the cosmos is both governed by laws and brimming with surprises, both comprehensible through science and forever beyond complete prediction. True exploration lies not in seeking what we already know, but in preparing for what we cannot yet imagine. When future astronomers look back on the mid-21st century, they may not recall the precise orbital parameters of FA22 or the exact light curve of Comet Cygnus, but they will likely regard 2025 as a pivotal moment, when humanity first truly grasped that we inhabit a universe of constant material and energy exchange, that our planet, our solar system, are inextricably linked to the vast Milky Way environment. In this era, when the Anthropocene is debated as Earth's new epoch, perhaps we must also acknowledge the dawn of a Cosmocene. Within this new framework of understanding, humankind is not merely a shaper of Earth's environment, but an active participant and responsible steward of cosmic processes. This role brings not only challenges and responsibilities, but also unprecedented opportunities to comprehend our place within the cosmos and discover our unique voice within the cosmic narrative.